University of Oxford, and she is going to be talking about contact tracing and trade-offs. So I'll pass over to you, Deirdre. Oh, Deirdre, I think you need to unmute yourself, sorry.
Thank you. Yeah, I just was saying thank you very much for the opportunity to be here and to speak on behalf of my research group, and always delighted to see so many participants. This is really fantastic. So looking forward to some good discussions later. In the interest of time, I've cut my presentation a bit, so very happy to take longer questions afterwards. So my group have mainly been working on contact tracing, and the reason for that was that we were brought into modelling COVID through RAMP, the Rapid Assistance in Modelling the Pandemic programme, where Petra at the London School reached out to our group to do some pieces of research, which I shall mention, and which we've been building on ever since. So most of the contact tracing work in our group has been led by Emma and Tim, who are, Tim is now at Imperial College London. And really the general question around contact tracing is, what are the most important characteristics to get the outcomes we want? And like everything in any infectious disease control programme, there are different aspects of the programme that can be tweaked. So we know that initially, certainly the test sensitivity estimates were low, but also that those vary through the course of infection. Historically, asymptomatic tracing has been a key benefit of contact tracing, but isn't really at the forefront of our contact tracing programme at the moment. It's very easy to overestimate the impact of contact tracing and try and understand in the models why that is and what assumptions are we making that are not really based in reality. And as has happened in many countries, there's a reliance in some places on tracing in a belief that it will solve the problem, but it really, a lot of modelling studies, we're not alone in this, has shown that it needs to be combined with social or physical distancing in order to really reach its maximum potential. And some work that I was involved in early with Matt and John about the large number of contacts, building on all the contact tracing work that has been done, contact survey work that's been done by this group and others, that you can end up having to manage very large case numbers if you include all contacts and do asymptomatic testing. So the way that we approach this, and this is built on the work of many other research groups as well, is that we use branching process models. This is where an individual case generates a distribution of offspring or people that they infect, and then those cases go on to generate their own distribution of offspring. And we're able to leverage some clever computational tools or clever analytical tools to analyze them. So in this example, we have, turn on the laser pointer, we have individual A, who is pre-infectious, pre-symptomatic, transmits to someone, then becomes symptomatic, transmit to somebody else, then they self-isolate and report to the testing. They're found to be positive, and so self-isolate for the rest of their infectious period. And we can include a lot of biological detail in these branching process models. And here we have an individual who is eventually traced. We have an individual who's never traced. And so you get onward transmission from this individual. And in this is just a toy example to illustrate how the model works. This individual is a false negative, and so they go on to infect other individuals. So we can simulate with these types of tools the size of outbreaks that you tend to get for different biological characteristics, different testing characteristics, and different characteristics of the test itself. So in this slide, I've just highlighted some of the methods that we've used for one particular publication, which is in medRxiv. And just to highlight that because we were brought in through RAMP, we're working with the London School has a number of publications on very similar models that we built on. And this slide is partly to highlight the fact that we can use a lot of detail about the biological processes. So for example, this is the probability of being symptomatic by day since infection. And this information has been changing over the course of the last year. And probability of transmission by day since infection, which again is changing. And our understanding of how viral load is linked to all of this is changing all the time, and it's a really fascinating area. And this, I've just included a couple of example results from this, from Emma and Tim's medRxiv paper, just showing you the fact that you have this enormous parameter space, some of which you know a fair amount about, but some of which you don't. And here we have the probability of a large outbreak as our main output variable. And here on this x-axis, we have what kind of coverage we have of contact tracing. So it's a combination of various things, but basically what percentage of people are reporting to contact tracing. And here on the top panel is an instant test, and here is a 2-day delay. And then these different colors are the different test sensitivity. So if we have an instant test, if there's no testing, it's quite similar to having a 95% sensitive test. So if we have a good test and we have no testing, we get similar results in terms of, so that's that the individual doesn't get tested, they just self-isolate for the whole period. Similar results in terms of the probability of a large outbreak. But here we find that if you have a bad test that has 65% sensitivity, if you test them on the day they arrive, you actually get higher probability of a large outbreak because you're going to have more false negatives. Whereas if you wait 2 days, so if it takes 2 days to get the results of the test, then actually these things start to converge. And even if the test isn't that great, because you've isolated all individuals for an extra 2 days, you're starting to get a similar probability of a large outbreak. And that is the problem for people reading contact tracing papers, is that these detailed assumptions make a big difference in terms of the outputs of the different models. And one of the things, again, that all the branching process models show is that superspreading, and again, I'm not going to go through all of these plots, superspreading is an inevitable consequence of infectious disease transmission, because you're always going to miss some cases. And the size of these superspreading events, so these very large events which happen, are dependent on the reproduction number in the community at large, but also these other characteristics of the testing program. And that's why it's really important that you get high levels of engagement with a testing program. So one of the questions that came out of that work, which came to us from Graham Medley at the London School and Lucy Yardley at Bristol, who's on SPI-B, which is the behavioural committee, was, would legally enforcing isolation reduce transmission? So now what you have is people who report to the system are legally required to stay at home for 10 days or 14 days, depending on the policy. And the important aspect of this, which the behavioural scientists, of course, identified, was if we do that, what if it's linked to a reduction in self-reporting? What if less people come forward as a consequence of the fact that they will be legally required to self-isolate? And so we used the same branching process model, and in this case, Tim led the work, and we investigated this effect. And this is one of the ways which SPI-M have sort of pioneered, the Ready Reckoner, as it's called, by Ellen Brooks Pollock and others, is to try and represent the big parameter space in a vaguely understandable way. So here on the different rows are the level of self-reporting. So we've got a high level of self-reporting down to a low level of self-reporting. The different columns are how long people isolate for, 1 day, 4 days, 7 days, or 14 days. And the x-axis, again, is this control effectiveness level, so what proportion of people report, etc. And then again, the y-axis is our probability of a large outbreak. And what could possibly have happened if you were to enforce isolation is that you would move to a 14-day isolation, but your levels of self-report would drop dramatically. And so you could end up in a situation where you had gone from a very low probability of a large outbreak to something 3 times higher. Now, of course, this depends on many different assumptions within the model, exactly this relationship. But these kind of results can be used to illustrate the fact that just because you pull one lever in the system, you may have unintended consequences on other levers in the system, which may mean that you're worse off. So in terms of the question that we were asked, does legally enforcing isolation reduce transmission if it's linked to a reduction in self-reporting? The answer was probably not. And that was, the parameters that we were using were based on kind of expert opinion from the behavioral scientists. And there is a growing body of evidence around this. This was a paper, I think, that came out in September, which showed, I think this is for self-isolation, people's intention to abide by the guidance in terms of, 70 to 80% of people were intending to isolate if they had symptoms, but actually of those people who did get symptoms, I think, only about 10 to 20% actually did so. And this is why, as in any infectious disease, human behavior is a really important aspect of all of these models. And it's important to understand as well the drivers of this behaviour. So the reasons that people left isolation were things like to get food, to help somebody else, or to go to work for their job. And it shows that those levers are actually really important levers to pull, and they're not epidemiological modelling levers, but we can illustrate the importance of that type of behaviour using the models. I'm very briefly going to mention one other project, but I'm going to wrap up in a second, which was also through RAMP. Petra asked us also to look at short-lived immunity, and this work was led by Thomas Crellin, who's a Wellcome Trust Henry Wellcome Fellow in our building, and he did some models looking at short-term immunity and simulated them within an age-structured model using, these contact tracing matrices, which have been so crucial to our understanding of this pandemic, and showed how the different dynamics of immunity in the different age groups will affect the dynamics of any. At this point, it was a resurgence in the winter, but as we look at variable vaccination rates and we look at variable prior immunity, what does next winter look like under different assumptions for how long immunity is going to last, and that's still something we don't know. So I think I'm going to wrap up with just 2 slides to note that this we're linked to some other research groups which also feed into our work. In particular, through the contact tracing work is linked with the Test, Trace and Isolate modelling grant, which is led by Liz at Manchester/London School. We're also involved in a project which is linked to Microsoft Research about providing access to models. And I think it's one of the exciting things about this pandemic is that a lot of code has been released, but also it's still challenging to provide people with access to those models because the people who are doing the modelling in anger are just so overloaded with work. And so it's a really interesting discussion to be part of, and we're very grateful for that opportunity. And then as a project that I'm very proud to be part of, but we haven't got many outputs yet, is working with some colleagues in Leicester on understanding the role of heterogeneous population groups, and in particular different ethnic minorities, on the dynamics of this pandemic. And of course, this is particularly important as we look at vaccination. So I've left a couple of discussion points here from some of our work, and I'll wrap up here. So where can contact tracing have the biggest impact as we get down to low levels of transmission, hopefully in the next few months? So in what ways should it be scaled up in order to drive down transmission in particular places? So which types of places can it be used? And which are the levers to pull in terms of including asymptomatic testing or targeting particular age groups, etc. And that just sits within a framework of the importance of understanding our behavioural response, trying to characterise it, trying to understand how different population groups respond to it. And then something that in particular Lee in our group is involved with is extending our branching process models to network models. And of course, the challenge, as all of you who work on network models, is how best to parameterize them. Can we include age-specific variability in risk and contacts? And can we maybe look at correlations between low vaccine uptake and transmission risk? But I'll finish there, and thank you very much, Kira and everyone.
Thank you very much, Deirdre. Thank you very much for everyone who's stayed with us for this quite long mammoth session.